Let's now continue on with a discussion of other ways you can develop parallel programs in Java. And this is going to focus on the parallel streams framework, which provides a synchronous parallel functional programming framework. And we'll talk about what that is. We'll also talk briefly about Completable Futures, which is an asynchronous functional programming framework. Those will be topics we'll cover later. You'll get a chance to play around with them and write some code to use them as well. These two functional programming frameworks leverage the object-oriented fork-join pool framework by default. With Streams, you're pretty much stuck using the fork-join pool. With Completable Futures, you can make choices about which one you want to use, but by default, it uses the fork-join pool as well. And that, again, is intentional because the fork-join pool, even though it's got some deficiencies with respect to the use of object-oriented design, is very optimized and very scalable. So let's talk about this. Modern Java, and by that I mean Java 8 and beyond, and we're now at Java 20 or something like that, so there's been a lot of evolution over the past decade, provides two primary functional programming frameworks. The first is parallel streams. Parallel streams allows us to take some data unit, data set, like an array or a list or a map or whatnot, and do some processing on it, the elements of that data structure, that collection in parallel. Here's a simple example that we will probably talk about later as a case study. This example takes a list of URLs to images that aren't already cached, we haven't already processed them, and it will then take those images, it'll download the images that aren't already cached, it will transform them to do image processing filters on them, and then it will store the images, and it'll do all this stuff in parallel. And you'll see tremendous speed up relative to doing it sequentially. And it's a really cool example of applying parallel functional programming with parallel streams. So basically what happens here is it partitions a stream up into multiple chunks, ultimately really each element in whatever data set you've got. Like, for example, if it's a list, it'll partition up into elements of size 1, and then it'll run all those things independently in different processor cores on different threads in the common fork join pool, and it'll combine the results or the sub-results into a single reduced result. So that's how the stream process works. And the chunks of data that it works on are mapped transparently to multiple threads and multiple cores, and therefore they can run in parallel. So all the threading abstractions and everything else, the forking and joining and so on, is all completely hidden from you, which is wonderful because it's often tedious and error-prone to program stuff like that. And as I mentioned before a couple times, Parallel Streams uses the Java Common Fork Join Pool because that's optimized for doing things in parallel on modern multi-core processors. So you can think about Parallel Streams as providing this wrapper around the fork join framework, the Common Fork Join Pool, that gives you fine-grained data parallelism using a functional programming model. So using the functional programming paradigm. So fine-grained data parallelism, functional programming, parallel streams. Let's talk about Completable Futures next. This is a very, very interesting framework, a bit different in many ways than parallel streams. It's asynchronous, not synchronous, and it kind of requires you to change the way you think about programming, although it tries to shield you from some of the quirks of asynchronous programming as much as it can. Here's an example. This is an example that we're going to walk through later in some detail where you want to be able to count the number of images in a recursively structured folder, like a website or a folder you might have on your computer, using asynchronous features that the Completable Future framework defines, the ability to be able to run things asynchronously and then be able to essentially chain and combine and reduce and so on, all the things that are happening asynchronously. Very, very, very cool example. So what it can do is it supports dependent actions that are triggered upon the completion of asynchronous operations. So what we do here is, for example, we start by asynchronously getting a web page at a given URL. Once we've got that web page, then we go ahead and create two tasks that asynchronously will count the number of images on the page and in parallel crawl all the links reachable from that page recursively. And when both of those asynchronous computations complete, we then combine the results to come up with a count of the number of images. And this is using something called completion stages. And we'll talk a lot more about this later. Really, really cool programming model, often the most efficient way of doing things. But most people haven't got their head around the patterns of effective asynchronous programming, so it takes a little bit longer to kind of understand how this works. But it's really neat, and it works very well. The basic idea here is you want to avoid having the caller block while waiting for the callee to complete the operation that it's running asynchronously and in parallel. And there's all kinds of goodness that comes from being able to do this, because when you're not blocking, you can go off and do something else. So this makes, for example, your systems more responsive, because you can start something running in the background and then wait for more input to come in and be able to appear to the user as if you're right there waiting for their next input, rather than having to have a dedicated thread that just waits for input and then processes it synchronously. So there's lots of neat things that come from doing this. Completable Futures can also leverage the Java common fork join pool. It doesn't have to. You can use other various types of concurrency. For example, you can use things like the Java cache thread pool or Java fixed size thread pools can be used. But most commonly, you just stick with the default, which is the common fork join pool. The Completable Futures framework, therefore, supports asynchronous parallel programming. And what I mean by that is you can have things running asynchronously, you can have lots of things running asynchronously, and then you can wait reactively for the computations to finish, once again, without blocking the calling thread, which is really cool. The metaphor I always like to think of when I talk about asynchronous programming is juggling. So anybody here who juggles, you know that the idea is to keep things up in the air as much as possible, be they tennis balls or bowling balls or flaming torches or chainsaws or whatever it is you're juggling. And you only grab the thing that you're throwing up in the air long enough to switch hands, or if you're really good, you throw it up again with the same hand, and then throw it back up and again. And that way you can keep more things in the air. So you can think of things in the air as being sort of like asynchronous computations that are running in the background, and you only need to wait long enough to grab them when they're done. So let's talk about the pros and cons of these frameworks. So first, the pros, they perform well on modern multi-core processors while also enhancing productivity. This is especially true of parallel streams. They're relatively easy to program, so that makes you more productive as a human. And they're relatively high performance, which means they take better advantage of the underlying computing resources, particularly the cores. They also encapsulate the object-oriented functional programming framework, that's the fork join framework, with these parallel functional programming facades, which is a big win. So you get the best of both worlds. You get performance from fork join pool, and then you get ease of programming by providing functional facades or wrappers around these things. You very rarely, if ever, need to have threads exposed directly. You don't have to create threads. You don't have to join threads. You don't have to stop threads. You don't have to synchronize anything. You very rarely need any synchronizers. And that ability to remove those types of programming concerns alleviates lots of complexities, both inherent complexities and accidental complexities, with concurrent and parallel programming, because you're letting the infrastructure do the work for you. You're not doing it yourself. Once again, there are some downsides to this. So one of the issues here is, out of the box, streams and completable futures are not fully integrated. You can use them together, but it's still a little bit of extra work, and it looks a little bit weird. It's actually a lot of fun to use it, but it's not as seamless as you might want. In particular, it doesn't, out of the box, achieve all the goals of the reactive programming paradigm, which focuses on responsiveness, elasticity, resilience, and message-driven designs. And we'll talk a lot more about that in the very next part of the lesson. Therefore, we have other frameworks like Java reactive streams, such as Project Reactor or RxJava, which integrates this concept of streaming and asynchrony far more intentionally, which is awesome. So that's what we're going to talk about next. So that's the end of our discussion of the parallel functional programming features that came into Java largely around the Java 8 timeframe.